Assalamualaikum, I am Afham and I will present about introduction. Since the realization in the negative impact of CFC refrigerants on the ozone layer in the 1980s, the research on the replacement of refrigerants has been a research hotspot in refrigeration systems. As a transitional substitute, HFC refrigerants have made significant improvements in protecting the ozone layer, but they can still exacerbate global warming, and HFCs will also face phase-out in the future. In fact, in order to decrease the leakage of refrigerants, the use of low-charge and efficient natural refrigerants in modern refrigeration systems has always been one of the research hotspots. In recent years, as the awareness of energy conservation and environmental protection has changed, the compact channel heat exchanger with high efficiency heat transfer characteristics will be further applied. As a natural refrigerant, ammonia is widely used in large and natural-scale vapor compression refrigeration or absorption refrigeration. It is currently a most common use refrigerant in industrial refrigeration. The application of ammonia mini-channel heat exchanger can break through the security restrictions of the ammonia refrigeration system on the application place. The development of ammonia mini-channel heat exchanger is very meaningful for the environmental protection and energy saving. Therefore, the research on boiling heat transfer in mini or micro channels has been receiving continuous attention. For the design and operation of ammonia two-phase flow mini-tube system, it is very important to master the characteristics of dry out and boiling heat transfer in mini-tubes.
Assalamualaikum warahmatullahi wabarakatuh. For the methodology, it uses the combination of indirect evaporative cooling to the mechanical vapor compression system, which is treats the outdoor air with high temperature and humidity. The wet channels are supplied with water which evaporates and absorbs heat from the air to further cool down the outdoor air. The pre-cooled and dehumidified outdoor air is then passed through the evaporator coil of mechanical chiller to further bring down its temperature and humidity to the desired values. The exhaust air leaving the wet channel is mixed with outdoor air and channeled to the condenser for the heat rejection. The room exhaust air is simultaneously heated and humidified in the wet channel of the indirect evaporative cooling, which recovers both the sensible and latent energy for pre-cooling and dehumidifying the outdoor air. The exhaust air leaving the wet channel is still colder than the outdoor air and it used as part of the cooling media of the mechanical vapor compression condenser to recover its cooling potential further. The sensible and latent potential of the room exhaust air is effectively reused, which will significantly reduce the overall energy consumption. That's all for the methodology. Thank you.
Hi everyone, my name is Farhan bin Noramiza. I'm going to explain the diagram and illustration. On the left, we can see the schematic of the combined IEC MVC system. On the right is the process demonstration in psychrometric chart. Usually, a psychrometric chart have more elements than this, but we only have 3 elements, which are saturation line, dry bulb temperature, and humidity ratio. First, we will look at the process for the room exhaust air. At the starting point, the room exhaust air is plotted here in the psychrometric chart, which is at 23 degrees Celsius dry bulb temperature and 11 gram per kg humidity ratio. As the air passes through the water film, it decreases in dry bulb temperature and increases in humidity ratio until it almost reaches saturation. This means that it almost reaches the most amount of water vapor per pound that can coexist with dry air at that temperature. After that, the dry bulb temperature and humidity ratio increases until the air has passed through the water film, where it now becomes wet air. The wet air will then be mixed with the outdoor air, where it turns to mixed air. As this happens, the wet air's dry bulb temperature increases while the humidity ratio decreases. The mixed air goes through the condenser where the dry bulb temperature increases and then be purged to the environment. And that is the process of the room exhaust air until it is purged to the environment. Now we will look at the outdoor air until room supply. At the starting point, the outdoor air will pass through the channel wall, where the dry bulb temperature decreases while maintaining its humidity ratio. After it has passed through the channel wall, it will become pre-cooled air. The pre-cooled air will then go into an evaporator, where its dry bulb temperature and humidity ratio decreases until this point here, where it will be supplied to the room.
Summary of finding, result and discussion. Indirect evaporative cooler (IEC) is a suitable and long-term alternative for existing mechanical vapor compression (MVC) chillers in cooling applications. IEC, on the other hand, is a passive cooler that has no control over the temperature or humidity of the supply air. IEC's effectiveness diminishes substantially when the air humidity is high. To overcome this limitation, the investigation of hybrid process that connects IEC and MVC is created. IEC performance. To simulate outdoor air, the environmental chamber supplies hot and humid air to the dry channels. When air leaves the wet channels, it is totally saturated, indicating that the latent potential from the room exhaust air has been effectively recovered. More importantly, a higher air temperature in the wet channels increases the saturation-humidity ratio and allows more evaporation, leading to more latent cooling effects which result in a larger drop of temperature in the dry channel. The energy consumption for the fans and water pump is fixed with the air flow rate. Thus, the higher the outdoor temperature, the higher the coefficient of performance is. Such a high coefficient of performance value is the result of effective, sensible and latent heat recovery from the room exhaust air. In contrast to the effect of temperature, a higher humidity ratio improves energy recovery efficiency. This is because higher outside humidity creates more condensation, which greatly enhances heat and mass transfer in dry channels. Energy saving potential. Comparing the coefficient of performance between hybrid IEC MVC with standalone MVC. When the outdoor air is dry, the overall energy efficiency is dominated by the coefficient of performance of IEC. Therefore, the higher the outdoor temperature, the higher the overall coefficient of performance. In contrast, the coefficient of performance of standalone MVC decreases with higher outdoor temperature as the refrigerant has to be compressed to a higher pressure for heat rejection. The coefficient of performance of the hybrid IEC MVC is up to 135% higher than that of a standalone MVC under a low outdoor humidity.